Just before I start, the sixth problem set is up on the homework site, our homework site, the Moodle site. It's about cell phones. So it's all about radio transmission and reception and stuff like that. And hopefully things that are vaguely relevant to you all, since cell phones are part of modern life. Where I left, and last thing is, I emailed all of you the booklets from the exam, from Friday's exam. All of the ones that I have, which include most of the ones from the SDAC, if that's you. They're out in these literature racks in the hall, and by last name, and I encourage you to pick up your exam. All right. So where I left off was talking about the process of launching an electromagnetic wave, which is done by moving charge around. And it will turn around that receiving the wave, a radio wave, involves the same thing kind of in reverse. So if you understand how transmitting a wave works, figuring out how receiving a wave works is easy peasy, or should be. And one of the devices that's used in the process of trying to launch a wave is a tank circuit. I talked about a tank circuit. The name tank comes from the analogy with water in a tank, sloshing a tank. A tank circuit is a system in which charge sloshes back and forth. And I use that term as though it were ordinary common language, but hopefully it makes sense to you that you have electric charge that's bouncing back and forth or sloshing back and forth. If I call it sloshing, it's followable. Any issues with that? Or questions about it? Okay. So a tank circuit is a resonant system. That is, it has a favorite frequency at which things rhythmically happen. You're familiar with resonant systems like the string of a guitar. You pluck it, it's got a frequency that's created by the mass of the string, the length of the string, the tension of the string. This is stuff that I do in the other semester, but it loves that frequency. And if you pluck it, of course, it goes that frequency. It's a little more complicated because it can go at other frequencies too if it behaves as multiple pieces of string. But it's got a resonant frequency. What else about it? Oh, if you were to sing at it at its favorite frequency, you can get it rhythmically moving too. And the physics behind that, I got the bowling ball pendulum. Didn't ask for it, but I've got the string without the pendulum so you can visualize the ball. The idea behind singing at a string and getting the string moving is that you can either give one of these resonant systems one mighty shove and get it going all at once, an act which involves doing work on it and giving it energy. You push it as it moves, you do work on it, but you also can push on it as it swings. So this is coming back and forth at me. And it's proving that pendula do not, their rhythmic frequency do not depend very much, a little here, on the mass of the object. So I'm working with the world's smallest pendulum bob. It's just a bolt. But I am adding energy to it a little at a time by giving it little pushes in sync with its motion. And if you've ever pushed a kid on a swing, you know all these tricks. You push the kid as the kid goes away from you to add a little energy to the kid every time it swings. So you push in rhythm and you get a big response. Is that okay? If you push alternatively at the opposite way, if you push as the kid comes toward you and let the kid do work on you, you suck energy out of the kid and gradually slow them down. Right? Why is this relevant? It's because the tank circuit has a rhythm too. And if you push it, if you push on the charge, give it a little shove with an electric field, for example, you can get the charge to slosh more and more aggressively in that tank circuit. In analogy with a tank, another one of these situations where you can give little pushes. The water in a tank, bathtub, for example, give it a little push, a little push. If you go in sync with its motion, you get the water going more and more aggressively. And these kinds of effects are useful in radio. So the tank circuit, just to remind you where the rhythm comes from. It comes from the tank circuit is built of only two components: a capacitor, which stores separated charge and therefore has energy stored in its electric field, and an inductor, again, a fancy name for an electromagnet. And an inductor is essentially a coil of wire, a piece of wire that carries electric current as opposed to storing separated charge. It carries current and it stores energy in its magnetic field. And the energy goes back and forth between these two components rhythmically. There are moments in which all the energy is in the capacitor in the form of separated charge. And separated charge is jargon for it has positive charge on one surface, negative charge on the other surface. They're separated, and no net charge. The sum is zero. So it's got energy in its separated charge, or the electric field, and that charge can get together, and basically the separation can vanish by having the current flow through the inductor, the electromagnet, and get rid of all the separated charge. So this is the moment at which all the energy is in the capacitor in the form of the electric field. And a little while later, after current begins to flow through the coil, you're at the opposite arrangement. There is no separated charge in the capacitor anymore. It's all gone. It's all canceled, if you will. And the energy is still there. It's in the form of the magnetic field in that coil. The coil is still carrying a large amount of current. In this drawing, I don't show you so much the currents there. What I do, there's the arrow is indicating current. This is actually a moment of peak current. There's no separated charge, but the current's whopping. And if you keep following this system for yet another portion of its cycle, the magnetic field will disappear and the electric field will reappear. And this just goes back and forth rhythmically. And I showed you an animation of this, and it's in the book as an animated figure. You can watch the charge work its way through the inductor, coming out of the capacitor, and then recharging the capacitor upside down and back and forth and back and forth. Any questions about the tank circuit's idea, behavior, anything? Okay. So it's rhythmic. The frequency of its behavior, that is, the number of times it reaches some part of its cycle every second. So in this case, we could decide that the part of the cycle we'll pay attention to is when the positive charge is on the top plate and all the energy is in the capacitor. That will happen. It happens now. The thing goes through its cycle, and then there's half a cycle I'm not showing you because this is recharged, but it's upside down. There's another half a cycle, and then it comes back to this arrangement. So if we watch this moment, it occurs now, and it occurs now, and now, and we count how many of those occur per second. Typically, tank circuits, it happens a lot faster than I can talk. So you watch it happen, and let's suppose it happens just over 1 million times a second, which is perfectly reasonable for one of these tank circuits. Then the tank circuit would have a frequency of just over 1 million times per second, or 1 million cycles per second, or 1 million hertz, again, is the shorthand name. It's abbreviated HZ. Do I care whether you know the name hertz? No, but it's just, okay. So tank circuits have a frequency. The frequency is determined by the characteristics of the capacitor and the characteristics of the inductor, how many coils they have, for example, on the inductor, the capacitor, how big the plates are, how close they are to one another. It's stuff that doesn't matter in this class, but you can adjust it. You can make tank circuits that only have a couple cycles per second. They're going to be physically quite big because they involve big coils and big capacitors. And you can make tank circuits that go many billions of times per second, and they're going to be little teeny because they have little coils and little capacitors. All right. So what I want to do next, so these are going to be useful in antennas, in radio transmission and radio reception as they appear here for both the transmission process and the reception process. In the transmission process, the act of sending off a radio wave often involves the movement of a lot of charge up and down an antenna. I'll come to antennas in a minute. And how do you get a lot of charge moving up and down the antenna? You don't want to just shove it up there every time with a battery. You take the battery, you shove the charge up the antenna, and then you turn the battery over perhaps to take the charge off. To do that every time, this is a heroic effort to get a lot of charge moving where you pay attention to it every single time. You can do it, but there's an easier way. And the easier way is to connect the antenna to a tank circuit and carefully get the charge bouncing back and forth, or sloshing, my preferred term, in the tank circuit, and connect that to the wire that is the antenna, and the charge bounces up and down the wire along within the tank circuit, and you don't have to pay attention to it every cycle. You can get it bouncing, and it will bounce naturally without your attention for at least a while. There's an issue of it replacing energy that goes into the wave it transmits. But as long as you do that, you don't have to pay attention to the motion of the charge. And you can add the energy, the makeup energy, the missing energy that's lost in the form of the radio wave. You can add that gently by giving it a push every cycle, like I was doing with the not-so bowling ball pendulum. Instead of having to push the charge up the antenna every time, you just let it bounce in that tank circuit and keep replacing energy in the tank circuit by giving it a little shove in rhythm with the charge motion. Is that questions about that idea? You let the tank circuit handle the big motion, the motion of lots of charge for you. One analogy in water would be you got a sloshing in a bathtub with a little water coming out, and you don't have to worry about splattering the water out there pulse by pulse by pulse. Just get the water sloshing. It's going to slosh. Water will come sloshing out of it every slosh, and you just have to sit there with a squirt gun, giving it a squirt every cycle to add in a little more water to keep the slosh and to replace the water that's lost, sort of. Okay, so we use tank circuits in the process of sending off the wave. It allows you to move a lot of charge up and down. And you need to move a lot of charge because the act of creating an electromagnetic wave is a little difficult. You want to move, the more charge you move, not surprisingly, the stronger the wave becomes. How much charge do you have to move to make a wave that's decently strong, like for transmitting music? You got to move a lot of charge, and you want help. Use a tank circuit. How about receiving? In the act of receiving the wave coming in, it is nice to have a device that is listening, in effect, for a very specific frequency. It has its own natural rhythm, and when it sees an electromagnetic wave with an electric field that's up, down, up, down, up, down, in sync with its favorite frequency, you get it's again like pushing the kid just in time with the kid's motion. You get a big response, a lot of motion in the kid on the swing, if you push them at the right frequency. If you push them at a random frequency, not much happens. The kid just gets sick to their stomach, right? But if you push them in sync with their motion, you can get them really going nicely. And that's what happens with a radio wave during the reception process. The radio wave is quite small. On the grand scheme of things, it's not a big influence. But it comes along, it's got an electric field in it, it pushes charge, and it can get charge. It can give charge a little push up and down an antenna, just a gentle one. And if it's connected to a tank circuit, and the tank circuit has that push frequency as its natural rhythm, you can get more and more charge bouncing up and down inside the tank circuit, and the result is large enough that it's easy for electronic devices to see. So tank circuits are used in the transmission process to move more charge, and they're used in the reception process to sense this very small, very weak influence by looking for it in rhythm with the tank circuit's motion. All right? How about the antennas? So the tank circuits, I would say, in the era before modern electronics, tank circuits were everywhere. Modern electronics can kind of sidestep tank circuits in certain contexts, and so they're still there. They're just not as absolutely essential as they used to be in radio transmission and reception. Antennas, however, are still pretty much essential, although even there, modern electronics have managed to sort of beat various constraints. And what an antenna is a tank circuit that has been stretched out straight. It behaves just like that. It has an aspect of it that's capacitor-like, and it has an aspect of it that's inductor-like. It's a tank circuit. It's just a straight one, which is bizarre, and I talked about it last time, but just to remind you that the ends of a wire, just take a single wire, ideally a pretty thin wire. If the wire is thick, so you're talking about more of a cylinder, like a can of soup, instead of a thin string, that changes the characteristics. You can make an antenna that's thick, but it's got slightly different characteristics. So let's just focus on a really thin one. The two ends, separated in space, separated by space, act as a capacitor. The fact that they're at opposite ends of the wire instead of on opposite surfaces of two plates doesn't really matter. It's still a capacitor. It still stores separated charge and has energy in its electric field. And the connection between the two ends is the inductor. It doesn't even have a single turn to it. It's just a straight line. So it's kind of like it's like a 180 degree. It's half of one turn and not even a bent one, pulled straight. But it still carries electric current and puts energy in its magnetic field. It's still an inductor. And the place at which the inductor ends and the capacitor starts at each end is fuzzy, doesn't matter. So they kind of blur together. It's still a tank circuit. It still has the behavior that there is a moment in time where you have all the positive charge at one end and all the negative charge at the other. There's no current flowing. All the energy is in the electric field between produced really by the positive charge. It points away from the positive charge toward the negative charge. So there's energy in the electric field. A little while later, as this charge rushes together, positive charge, negative charge, separated by a wire, they want to get together, and they do. So there's current flowing in the wire, and during that moment, the amount of charge at the ends, or in the capacitor, decreases, ultimately to zero, and the energy in the magnetic field of that current connecting the two, that magnetic field energy becomes basically, it's all the energy that this antenna / tank circuit has. So the energy goes back and forth. And I showed you the animation. I'll reprise the animation. Here it is. This is showing you the slosh. So it's a wacky straight line tank circuit. And the rhythm of this tank circuit is such, wow, boy, this is called a half-wave antenna because the physical length of that wire is half as long as the wavelength of the electromagnetic wave it creates. So there's a so what I'm doing is I'm thinking out loud here. The frequency of this thing it's the speed of light divided by twice the length of that wire. I think I got that right. That tells you the frequency of this antenna. The point of that really, the factor of the 2 in there is because this is what's called a half wave. It's half as long as a wavelength. I don't want to update Java. I know software is more important than anybody else. Go away. Okay, so the sloshing it's proportional to 1 over the length. The frequency is proportional to 1 over the length. As you make the antenna shorter, its sloshing frequency gets faster. So the higher the frequency of the system, of this tank circuit, and ultimately of the electromagnetic wave it will launch, is proportional to 1 over the length. So if the shorter the antenna, the higher the frequency. Or taking another direction, the lower the frequency, the longer the wire has to be. You okay with this so far? This is called a half-wave antenna. What's the point here? This is a structure that is resonant at a certain frequency, and if allowed to launch an electromagnetic wave, which I'll wave my hands on in a moment, it will produce a wave with this frequency, the frequency you see here, and it's resonant. Yeah.
So if it's like, if you're using it to listen to the radio, then there's like, how much does the length of the antenna impact?
How much does the length of the antenna impact the music you're hearing to, the frequencies and stuff? It specifies the frequency to a large extent. That is, if you want to listen to, and I'll put the numbers in and hopefully they're followable. If you want to listen to 100 million cycles per second, a radio wave that's coming along at 100 million cycles per second, which sounds like I pulled it out of thin air, but that would be in the FM radio band. It's allocated to the FM radio band. That would be 100.0, WABC, or no, pick some non-chosen, WLOU. 100 million cycles per second. Is that okay? To launch that wave not only is 100 million cycles per second, but it has a wavelength of 3 meters. How do I know that? It's because I told you that the product of the frequency times the wavelength is the speed of light in empty space. And I know the speed of light is 300 million meters per second. Well, if there are 100 million cycles per second, I need 3 meters to multiply that by to get 300 million meters per second. So 3 meter wavelength for 100 million cycle per second wave. So that's the width of this bench. That's 3 meters. Pretty close. This one up here. Is that okay with everybody? To make a wire antenna that is resonant at 100 million cycles per second, you want it half as long as the wavelength of the wave. You want it this long, like that. So it's actually sort of 2 halves. It's got a half up and half down. So think of it as two quarter wave pieces, quarter wavelength pieces. You make one of them go positive and the other one go negative, and then you reverse them. I've drawn it as a single wire, and that's fine. If you think of a single wire, it's going to go from positive up, negative down to negative up, positive down, and back and forth. That will be resonant at 100 million cycles. If you want to launch a wave that is 106 million cycles per second, you want to make the antenna a little shorter to make it resonant. So the length of your antenna brings it into resonance with the wave that you're trying to transmit, and ultimately you're trying to receive also. If you shift the length of the wire, it won't be as good at transmitting the wave or at receiving it, because it won't be in resonance anymore. It won't move the charge naturally in the right rhythm. It will be fighting you a little bit. It's like pushing a kid a little too many times per second in their swing. You're not going to get them swinging all that hard. You're going to drift in and out of sync with them in effect. And so this does matter. In FM radios, at least used to have, here's one, telescoping antennas like this thing. The proper length is longer than this. This is too short. This is not resonant. They may be playing tricks to get it to be resonant. There can be hidden stuff underneath there that helps. But really, if you want to really get a good signal, be resonant. But they can't make it resonant for all the frequencies on the FM dial. So they go for sort of the center, and then they either play tricks trying to help bring it into resonance, or they just deal with the fact that it's simply not quite right. And they can live with that if they're clever in the electronics. Is that okay? Other questions about this? This antenna, you can call it a half-wave antenna. A half-wave antenna is just naturally resonant at the right frequency to produce a wave that is twice as long as it is in wavelength. I mean, the language here is, I get all tongue-tied in it. If you want to make it slower, make it longer. If you want to make it faster, make it shorter. Is that okay with everybody? The amount of charge you move up and down, if you increase that, you get a stronger wave coming out of it. Let me again wave my hands a little bit and show you why a wave gets launched by this guy at all. And that is, there is a vertical electric field here created by the fact that you've got positive charge above negative charge or vice versa. So it's not surprising that there is a predominantly vertical electric field present whenever there's a separation of charge. And there is a weird circling horizontal magnetic field caused by the flow of current through that wire. The point of haranguing about that is that the electric field is predominantly vertical, and the magnetic field is predominantly horizontal. That should sound familiar because electromagnetic waves have that perpendicular arrangement. And the two fields with the same rhythm, electric field, magnetic field. What you ultimately want to launch is a pairing of those two fields that travel together, recreating one another. And these fields, as they are right there, are not exactly that field, but they have a piece of them that is like that. And they launch, what comes roaring out of this, predominantly in the horizontal direction, is an electromagnetic wave. It travels radially, again, to use the language that's familiar to, at least to physicists and hopefully engineers. It travels out the radial direction, away from the center. That wave travels out mostly horizontally, and it has a vertical electric field and a horizontal magnetic field. It is what we've called a vertically polarized wave. So this thing transmits a vertically polarized electromagnetic wave. I told you what those were. I hope you remember them. To transmit a horizontally polarized wave, which the electric field is horizontal, what do? Rotate that wire 90 degrees so that it is itself horizontal. That will radiate a horizontally polarized wave. This vertical polarization, however, is more common and more useful because the strongest part of the waves that come out of this, remember, waves ultimately are three-dimensional things. They go off in all directions. They're worse even than waves on water. Waves on water are at least two-dimensional because there's a surface, but waves in electromagnetic waves travel in three-dimensional space. They're three-dimensional, messy things. The strongest wave comes out horizontally. In all directions, actually. It's symmetric. The wave comes roaring out to the right and to the left and toward you and away from you and everything in between, all the horizontal directions. That's the strongest transmission direction. There is some wave coming out of this antenna heading upward a bit and downward a bit, but it gets weaker. It depends on trigonometric functions. Not surprising, trigonometry actually shows up in the real world. I think it goes, yeah, I'm not going to do it. It's a cosine squared or sine squared distribution. There is no wave that comes out vertically off the top of the antenna. It hits exactly zero strength vertically or downward vertically. And so my joke last time was that there's nobody out there by and large. A plane flying right over the antenna, you look down, whoa, we're going right over that antenna, look at that. You can't get any reception there. That antenna is not sending any electromagnetic wave at you. The strongest is horizontal. And that's really nice for earthbound radio stations. They do want to send out the wave predominantly horizontally because that's where the people are. No joke. If they tip their antenna 90 degrees and send out a horizontally polarized wave, the wave is strongest perpendicular to the antenna, which includes horizontal towards you and horizontal away from you, but it also includes up and down, which are kind of useless. Nobody's there, and the people at these ends won't get any reception. So most antennas, there's a bunch of reasons not to have antennas horizontally in many circumstances. There's a lot of power is sent in places where there's nobody, namely straight up and straight down and everything close. And there are places where there's no radiated wave, and no power in the wave. So why do that? So this is why a lot of antennas that you see for transmission are vertical. So is that okay so far? This antenna, I told you, it's called a half-wave antenna. It has the characteristic that one tip goes to high, it gets packed with positive charge, and the other one gets packed with negative charge. That's a polarization, right? You can talk about it having poles. They're not magnetic poles, they're electric poles. But it's got a positive at one end, negative at the other, and then vice versa, back and forth. It's given the name it's often called a dipole antenna because it's got two poles, one up, one down, they go opposite directions. So the name is dipole, and I won't justify that since it seems to sound magnetic, but it's not. The voltage at the tips goes very high positive, very large negative, and then then reverses. So you don't actually want to touch the top most of the time because it's high voltage, it's dangerous. And that includes the top and the bottom. There is one point right dead center where the voltage never strays from 0 volts. It's always 0 volts there. And that's usually where the connection to the radio station's transmitting system is placed, right there. Where the voltage is 0, you just move charge from one of the ends to the other. So you can sort of think of it as two separate pieces with an electrical connection at the joint where it's convenient to work with because the voltage is always small or 0. This antenna is used in cases where the radio wave has a high frequency and therefore short wavelength. You can build both of those ends nicely. You can work with them. You go in the middle and you put in you do all the work at the middle and the ends go to high voltage one way and the other. For lower frequencies, this is a problem. That structure gets very long and it's got dangerously high voltage at the top and the bottom, so you don't want to touch it. And you have to do all the work of the radio station work at the middle. So you wouldn't really want to build a vertical structure that you have to go connect at the middle of it, which might be 100 feet up, and you have to protect the bottom so no one touches it, because it goes up and down to 100,000 volts maybe. It can go way up and down in voltage. Lightning bolts can come out of it, so don't touch it. So what do? People make use of a nice trick, and that is this one. What is this? Let me just stop it for a minute. This is what's called a quarter wavelength antenna. It's only half as long, but it is above a conducting surface. And that conducting surface, like metal, that conducting surface acts as a mirror. And if you put a vase on top of a mirror that's sitting on a table, you put a vase on it, and you look in the mirror, you realize, oh, there's a second vase here, upside down in the mirror. And sort of the Alice in Looking Glass world, that has real consequences. That reflection you're seeing has real consequences. In the case for the vase, for all practical purposes, if you look at that vase, all the light coming out of it has all the right characteristics of being a real physical vase, just not really there. And the same thing is true here. You put that quarter wave antenna on top of a conducting surface, and the reflection in the mirror has all the characteristics of the upper half of the antenna, with one interesting feature about it that's different. When there's positive charge on that upper quarter wave antenna, there is negative charge on its reflection. And why would that be? Well, because the positive charge attracts negative charge toward it, and that's where the negative charge ends up in that reflection. So the point is, the quarter wave antenna, which in principle has to be above a conducting surface, like the top of your car or the surface of the earth, which is a decent conductor, it can do it. The quarter wave antenna creates in the mirror reflection the other half of the full dipole half wave antenna. It's half as long, but it has all the action. Not only that, but at the bottom of the antenna, I point at my screen here as though that's helpful for you. At the bottom of the antenna, this is the point at which the voltage is essentially 0. That's the high voltage end. In this case now it's large negative voltage, and that's large positive voltage. This is the nice safe one that you can touch and not worry so much about. This is where the radio station wants to be doing all its electrical work, and it's near the ground. So if I let this go, it has the same rhythm, the same behavior, all the same features as the full-length antenna, but it's only half as long and so on. You okay with that idea? It's called a quarter wavelength antenna because its resonant frequency, its favorite frequency, corresponds to an electromagnetic wave that is 4 times as long as it is in wavelength. So lots of situations in which people use quarter wave antennas. The interesting electrical connection is at the bottom, where the voltage is very small, the current is large, the voltage is small. This is a quarter wave antenna here. In reality, this is too. I mean, there are just lots of quarter wave antennas. The ones on top of your car, quarter wave antennas. They can make them shorter than physically a quarter wavelength by adding more inductor somewhere. How do they, the bigger electromagnet, how do you do that? Put some turns in the antenna. So they'll hide turns that you can't see. Or you may, sometimes you do see them. You'll see an antenna sticking out of a car and it has some curls in it. They're effectively adding length to the antenna with those curls. More inductor, lower frequency. Instead of going longer, they're going squirrely. Questions about any of this so far? What are your takeaways at this point? Is it the low frequency radio waves, which are associated, any frequency, an electromagnetic wave can have any frequency you like, from 0.000001 cycle per second to trillions of cycles per second. The whole thing is available. The countries of the world have sort of chopped up parts of this range of possibility and allocated them to certain activities. Your cell phones, for example, use certain patches, certain ranges of frequency, and are forbidden to go outside those because they'll interfere with some other activity. What is called AM radio uses both a technique that I'm going to talk about shortly about how to convey music or sound information. Not only does it use that, it also has a certain range of frequencies, and they're low frequencies by radio wave standards. They're in the vicinity of 1 million cycles per second. I said it last time, it's 550,000 cycles per second to 1.6 million cycles. That's what they got to work with. Those are low frequencies. They require very long antennas. You wouldn't want to make the antennas very long and horizontal because you'd take over somebody's entire neighborhood. You also would then be transmitting most of your power in this slice of the world, which includes the sky, which is not very good. So don't do that. Go vertical. And they don't really want to go vertical and be 300 meters long. That's, plus with the radio station's connection being in the middle of that, that might be a couple hundred feet off the ground. So what do? Go to a quarter wave antenna. Use the fact that the Earth is electrically conducting and just have the upper half, the quarter wave component. So that's what most AM radio stations use, a vertical wire that is the quarter wave antenna sitting above the conducting Earth. They send out a wave. Because the charge is moving up and down, the electric field in the wave is vertical. The magnetic field is horizontal. They're sending out vertically polarized electromagnetic waves. They are strongest horizontally. If you start going over the antenna, kind of, you get weak waves, so you don't get reception up there. That's the story of AM radio, apart from the information transfer. Okay? FM, the FM band, which uses the FM signaling technique for conveying information, but also has been allocated a range of frequencies from, I think, is it 88 million cycles per second to 108 million cycles per second, something like that. Much higher frequency. Vicinity of 100 million cycles per second. The wavelength of those waves is only about 3 meters, as opposed to 300 meters for AM. So only 3 meters, well, 3 meters, you can do whatever you like with the antenna. If it's only got to be in the vicinity of 3 meters, actually, you don't actually want 3 meters, you want half that. So you can make a dipole antenna for FM radio. You can make the top half and the bottom half, no conducting surface. You can do that, and they probably do. For 100 million cycles per second, you want that antenna to have, the full length is 3 meters, that's the wavelength. The half wave antenna would be 1.5 meters, and the 2 quarter wave pieces would be 3/4 of a meter, about that long. So there's the upper half is this big, the lower half is that big. You can not have the lower half by putting a conducting surface here, or you can have both. And it's not so bad having both of them vertical or horizontal. It's okay, you can do it. And I think to an extent they do. They transmit both horizontally and vertically polarized aspects of the wave. And the value there is simple. Another thing I haven't talked about, but we'll do. With the AM radio, where they only have a vertical antenna, straight up, and they transmit a pure vertically polarized wave, if you want to receive that, first off, you need a long antenna, which is a problem already. But I'm going to leave that aside for the moment. But you also have to be pretty careful how you're detecting the wave, because if you want to look for motion driven by electric fields, you better be looking with a vertical piece of wire, because a vertically polarized wave, that is with an up and down electric field, is not going to be able to push electric charge across an antenna. So if this is the antenna, the world's first wood antenna, okay, a vertical electric field will push charge up and down this thing nicely. But a vertical electric field will not do much for this thing. Knock my glasses off. Because the charge can't move off the wire. So you won't get any reception like this. So you got to be vertical. So the orientation of an AM radio antenna matters a lot. Is that okay with people? The details, they're details. But for FM transmission, if they transmit, and I think they do. I look this stuff up and forget it so often. I'm currently in the forget cycle. It's not fun if you're driving along or you're walking along with your FM radio and you tip the antenna for some reason and everything goes away. So what do? They transmit both vertical and horizontal. And now, whatever you do with your antenna, you still get some charge motion. It's okay. You still get the signal. So they try to make life as easy as possible for people. Having only talked about this, let me just show you that this is real. This is a little transmitter. It has a tank circuit, which is drawn here in the language of schematics and electrical engineers. But it has a tank circuit here, and this is the inductor part. It's half a turn of wire. That's the inductor. Sorry, it's not much of a coil. It's a little itty bitty piece of coil. And I've now got it active. And what is happening now is current flowing back and forth, back and forth. There's a capacitor inside this, so the charge is sloshing back and forth and back and forth. And as the current goes back and forth in this wire here, it has a magnetic field that first curls around the wire one way and then the other way and back and forth. And that changing magnetic field right here creates an electric field that pushes charge first up this wire. This is a transmitting antenna, and down that wire. This thing is resonant at the same frequency as that inductor. And so the charge is sloshing up and down this thing. This is the point of zero voltage on a dipole antenna. This is or half-wave antenna. So it's going from positive charge up, negative charge down, to negative charge, back and forth and back and forth. And this is the receiving antenna, also resonant. And do you see the light bulb glowing? There it is. It's glowing because the charge is being driven up and down this resonant object as well, and lighting up the little light bulb. And as I've claimed that the electric field's all vertical here. This is a vertically polarized electromagnetic wave that's coming out. It gets weaker with distance. I mean, it can barely receive it out here. But if I go in close and it's nice and bright, if I go at right angles, look what happens. As claimed, you can't receive a vertically polarized wave with a horizontal antenna. The charge is just pushed across the antenna and doesn't have any, nothing happens. You got to be vertical. Can you see the light bulb? Is that? Okay, good. So we're transmitting the thing. In principle, above it, we'll have nothing, and that's basically true. You gotta be somewhere out here. Why is it not here? Probably I'm getting too close to the transmitters, messing stuff up. All right, so that's a transmitter there. I'll turn this guy off. So half-wave antennas, quarter-wave antennas, mixtures of the two, the relationship between the frequency and the lengths of the antennas. And so a lot of the modern communication, Wi-Fi, your cell phones, all that territory, very high frequencies. Frequencies that were not possible 40 years ago because electronics couldn't work with things that change that fast. Modern electronics can. Very high frequencies, therefore very short antennas. So the antennas in your cell phone, the early cell phones or early radio phones had big antennas. Now, the current ones, they're tiny because the frequencies are so high. The antennas only have to be this long, or you've seen Wi-Fi antennas. Those are quarter-wave antennas. They're little guys. And that's enough. Okay, what I wanted to try to convey now is this signaling techniques. A radio wave is all in good. By itself, though, it doesn't have anybody's voice associated with it. It doesn't have any music. How do you do that? Well, the way in which you put, of course I did the way in which you encode information of any type, including sound information, is by changing the wave with time. So create the wave. If it's smooth and steady, same strength, same frequency all the time, it's too simple. It doesn't say anything, or it doesn't contain any information. But if you play with it, the wave, so the wave varies with time in some important way, now you can actually send signals. It is very much like smoke signals. If you just got a burning, smoking fire, up goes the smoke, it says nothing. But if you begin to blink the smoke on and off, change it with time, you can send out signals, or Morse code, same idea. Is that okay? So there are the two simplest ways in which to play with the radio wave and convey information are what are known as amplitude modulation and frequency modulation, or in short, AM and FM. AM says we can convey information to the distant radio receiver by blinking. It's like smoke signals, making our radio waves stronger and weaker as a function of time. And if you go up and down in strength, which you do by moving first more electric charge up and down the tank circuit antenna, and then less charge up and down that tank circuit antenna. So shift the amount of charge, make it fluctuate with time. If you make it, you can use that fluctuation in amplitude, the strength of the wave, to signal the air pressure that was observed near the microphone of somebody talking. So as they talk, and the air pressure from their voice fluctuates between high pressure, low pressure, a little bit around ambient, the normal pressure. Those variations in air pressure can be represented as variations in the strength of the radio wave. Your questions about that idea? You want to represent high pressure? During one moment of someone's voice, there's high pressure. You represent it by boosting the strength of the radio wave. You want to represent low pressure? Weaken the radio wave. And do this in nice proportion with the air pressure fluctuations, and it conveys all the sound information. So the radio wave then is carrying the information it needs to represent sound. It's not literally carrying sound, it's carrying the information. And a radio receiver can use that information. It can watch the charge moving up and down in its resonant antenna and say, oh, it's extra strong right now. That means that's a high pressure moment in the voice. And so, oh, there's less charge moving up and down. That's a low pressure moment in the voice. And it can reproduce the voice. Is it okay so far? That's AM modulation. I'll come back to it, but I'll also show you FM modulation. FM modulation is another approach. Don't wink the radio wave up and down in intensity. Wiggle it back and forth in frequency a little bit. Make the cycles a little faster than normal or a little slower, and you can use that to represent sound pressure. And you can again convey sound information, not sound itself, but sound information as these subtle changes in the radio wave you're constructing. And so I'll come back to those and talk a little bit about how FM is typically better than AM for good reasons, and then we'll move on to microwave ovens.